Imagine stepping into a doorway here on Earth and instantly emerging on the other side of the universe, bypassing millions of light years in a single moment. It sounds like science fiction, but according to modern physics, something like this might actually be possible. Today, we're going to explore how wormholes theoretically work, what science says about them, and whether humanity could ever use them. Before we dive in, make sure to like this video, subscribe to the channel, and turn on the notification bell so you don't miss any future deep space explorations. The idea of wormholes begins with gravity, but not the everyday gravity you experience when you drop your phone. In modern physics, gravity isn't really a force pulling objects together. Instead, it's the bending of space and time itself. This concept comes from the theory of general relativity, developed by Albert Einstein in 1915. According to general relativity, massive objects like stars and planets warp the fabric of spacetime, creating curves that other objects follow. A common analogy is placing a heavy ball on a stretched rubber sheet. The ball creates a dip, and smaller objects roll toward it, not because they're pulled, but because the surface is curved. Once scientists realized spacetime could bend, the next logical question was whether it could also connect distant regions directly. In 1935, Einstein and physicist Nathan Rosen explored mathematical solutions to the equations of general relativity that described what became known as Einstein-Rosen bridges. These bridges are what we now call wormholes. The concept is surprisingly simple in theory. Imagine spacetime as a sheet of paper with 2 points drawn far apart. If you fold the paper so the points touch, you can connect them with a tunnel that's much shorter than traveling across the surface. A wormhole is essentially that tunnel, except instead of paper, it's spacetime itself. However, theoretical existence doesn't automatically mean practical possibility. Early wormhole models had a major problem. They were unstable. The moment anything tried to pass through, the wormhole would collapse faster than light could travel across it. This meant that even if wormholes formed naturally, they would be useless for transportation. For decades, they remained mathematical curiosities rather than realistic possibilities. Things changed in the late 20th century when physicists began investigating whether wormholes could be stabilized. One of the key figures in this research was Kip Thorne, who explored whether exotic forms of matter could hold a wormhole open. Exotic matter doesn't mean alien material. It refers to matter with negative energy density, something that behaves very differently from anything we encounter in daily life. Normally, energy is positive and gravity attracts, but negative energy would create repulsive gravity, pushing spacetime outward instead of pulling it inward. In theory, placing negative energy at the throat of a wormhole could prevent it from collapsing, allowing safe passage. Interestingly, negative energy isn't purely hypothetical. Certain quantum physics effects suggest it might exist in tiny amounts. One example is the Casimir effect, where two extremely close metal plates experience a small attractive force due to quantum fluctuations in empty space. This effect can be interpreted as a region of negative energy density between the plates. The amounts involved are incredibly small, far beyond anything needed for a human-sized wormhole. But it demonstrates that physics doesn't completely forbid the concept. To understand how wormholes might function, it helps to think about spacetime not as static, but dynamic. In general relativity, spacetime can stretch, compress, twist, and connect in complex ways. A wormhole would have two mouths connected by a throat. Each mouth could exist in different locations in the universe, or even at different times. That last possibility is particularly mind-bending. If one mouth experienced time differently than the other, perhaps due to traveling near light speed or being placed in a strong gravitational field, the wormhole could theoretically become a time machine. Enter one side and exit in the past or future relative to the outside universe. This possibility raises enormous paradoxes. Time travel could allow someone to change events that already happened, creating logical contradictions. Because of this, some physicists suspect that unknown laws of nature might prevent time-traveling wormholes from existing. The physicist Stephen Hawking proposed the idea of chronology protection, suggesting the universe might have built-in mechanisms that prevent time paradoxes, possibly by destroying wormholes before they become time machines. Another important question is whether wormholes could form naturally. Some theories suggest they might appear at extremely small scales due to quantum fluctuations in spacetime itself. At the Planck scale, which is unimaginably tiny, spacetime may not be smooth, but instead frothy and chaotic. sometimes called quantum foam. In this picture, miniature wormholes could constantly form and disappear. However, scaling one up to a usable size would require immense energy, likely far beyond anything humanity could generate with current or foreseeable technology. There are also speculative ideas involving black holes, because black holes involve extreme space-time curvature. Some scientists have wondered whether certain black hole configurations might connect to other regions of the universe through wormholes. However, the simplest black hole solutions don't produce traversable wormholes. Instead, they lead to singularities where physics as we know it breaks down. Still, advanced theoretical models sometimes explore rotating black holes or quantum gravity effects that might change the picture. Wormholes have captured public imagination, largely through science fiction. A famous depiction appears in the film Interstellar, where astronauts travel through a wormhole near Saturn to reach another galaxy. What's remarkable is that the visualization in that film was based on real physics calculations provided by Kip Thorne, making it one of the most scientifically accurate portrayals ever created. While still fictional, it reflects how seriously scientists consider the mathematics behind wormholes. If wormholes were possible and controllable, the implications would be enormous. Interstellar travel could become practical, allowing journeys that would otherwise take thousands or millions of years. Communication across cosmic distances could happen instantly. Entire civilizations might connect across galaxies. Even more dramatically, wormholes could change our understanding of causality and time itself. The universe would become not just vast, but navigable in ways we can barely imagine. But there are huge challenges. First, creating or finding a wormhole would likely require energy comparable to that of stars or black holes. Second, stabilizing it would require exotic matter we don't know how to produce in large quantities. Third, controlling where it connects would involve manipulating space-time geometry with extraordinary precision. And finally, we don't even know whether unknown quantum gravity laws might forbid traversable wormholes entirely. Modern physics is still incomplete, especially when it comes to unifying general relativity with quantum mechanics. Some cutting-edge theories suggest wormholes might be deeply connected to quantum entanglement, the mysterious phenomenon where particles remain linked across distances. A provocative idea, known as EPR, proposes that entangled particles might be connected by microscopic wormholes. If true, it would hint that space-time geometry and quantum information are fundamentally related. This remains speculative, but it shows how wormholes sit at the frontier of theoretical physics. Another fascinating possibility is that advanced civilizations, if they exist, might create wormholes as cosmic infrastructure. Some scientists have even proposed searching for observational signs of artificial wormholes, such as unusual gravitational lensing patterns. So far, no evidence has been found, but the idea illustrates how wormholes move from pure fantasy into the realm of scientific investigation. Ultimately, wormholes represent both hope and mystery. They show that the universe may be far stranger than our everyday intuition suggests. Space and time might not be rigid barriers, but flexible structures that could, under the right conditions, connect distant places instantly. Whether humanity will ever harness such phenomena is unknown, but exploring the possibility pushes physics toward deeper understanding. So the next time you look up at the night sky, remember that the distance between stars might not always be as impossible as it seems. Somewhere in the equations describing reality, shortcuts through space-time might exist, waiting for a civilization advanced enough to discover them. If you enjoyed this journey into theoretical physics, don't forget to like the video, subscribe to the channel, and turn on the notification bell so you never miss another exploration of the universe. Thanks for watching, and see you next time.